Now, the last thing I want to talk about before we start doing some problems with the diesel cycle is about how I've been talking about the ideal diesel cycle. And remember, the ideal diesel cycle is simply saying, well, I might have a PV diagram that looks something like this. Let's make sure I draw it right. And this is for the actual. But I'm trying to idealize it because I can't do real easy math using that diagram. And so what I do is I change it to a constant, that's constant volume, constant pressure, isentropic expansion, and then we have constant volume heat rejection and isentropic compression. So I match it as best I can. Now, if my architectures are changing and the way the engines are running are changing, then as I get newer or at least higher, more efficient systems, I'm going to have to change how I'm idealizing things. And that has happened. So in modern high-speed diesel engines, I actually have fuel being injected much sooner into the combustion chamber. What I mean is this. Here's my piston. I have my piston right here. This right here is the top dead center line. Here is bottom dead center. What's going to happen is that fuel is going to be injected before I get to that top dead center line. You're like, wait a second, wasn't that the whole point of diesel engines, is to not have that fuel be injected where it can auto-ignite? Well, yes, we want to get it compressed as much as possible, but in these high-speed ones, they're having to inject it earlier because the fuel has to mix. And it takes time for it to mix. Because it takes time for it to mix, I have to ignite it faster because this guy moves very, very, very fast, up and down, up and down, up and down, again and again and again. Now, what does that do? Well, because I have an air-fuel mixture now here that is being compressed, that's exactly like the Otto cycle. So you're like, okay, so it's just turning into the Otto cycle. Not quite. So let's go ahead and draw this PV diagram again. Start here, isentropic compression, that's all good. So for this distance right here, however far it moves and actually compresses an air-fuel mixture, not just an air mixture, it is, just like the Otto cycle, going that at constant volume. That's what we're assuming there. As a note, this distance is very, very small, okay? It's not actually a big distance. But this is a diesel cycle, which means that that air-fuel mixture is igniting over a longer period of time, so it's also continuing to ignite even as this guy is moving down. And so this distance right here, when it's moving down, is constant pressure because the piston head is able to move down. It's going to move down the entire time. So we have a different cycle here, okay? We have a different cycle. We have two processes that are making up our heat addition process rather than just one. That's the better way of looking at it. So let me show you a nicer picture of that because my drawings only go so far and we can talk about it more. So here it is. We have our PV diagram. You can see this is before it hits top dead center. I'm just going to say point X is kind of like where it hits top dead center. This is before, this is after, because the combustion is happening both before and after in part, and that is leading to it having multiple different cycles. We're just doing this because we're trying to make it match the actual cycle as close as possible. And this is what's called a dual cycle, which is better for high-speed compression and ignition engines. This won't be the case for all engines. If I don't mention it being a dual cycle or give you some other clues that it's a dual cycle, you will just treat it as a regular ideal Otto cycle, which looks like this guy here. Once again, if you don't have a flip book for all your cycles, I strongly suggest that you make one just so you can have all these pictures and you can use it when you're solving problems. Okay, we'll stop here. I know this is a short video, but I wanted to give you one little extra detail about these idealizations. And next time we're jumping into a problem. So I'll see you then. Bye-bye.